We present a behavioural transformer for effective collaboration between a robot and a non-stationary human. I'm Ruaridh at the University of Edinburgh and supported by the Robotics CDT. Imagine a collaborative game of tennis where two players are working together to pass the ball between themselves. Humans are effective at adjusting their behaviour to collaborate well together. In this work, we are interested in the question, how can robots collaborate with humans dynamically changing their behaviour? As an example, let's say the human wants to pass the ball to the robot in a particular location. To collaborate effectively, the robot must predict the human's target to intercept it at the right moment, as reactive behaviour may not suffice due to the speed of the ball, motor lags and time of travel. Several factors influence the human's intended target, from short-term influences such as the robot pose to long-term influences like the direction of previous hits. We achieve efficient collaboration by adjusting the robot's actions according to the predicted target. Our framework is based on reinforcement learning that provides a powerful structure for decision-making processes and facilitates optimal decision-making in static environments. In human-robot collaboration scenarios, the human is typically considered part of the environment, which makes the dynamics time-dependent due to the human behavior changing over time, and leads to traditional approaches producing suboptimal results. This is known as non-stationarity and is the problem that is being addressed in this paper. Related work aims to learn high-level human goals using feed-forward or recurrent neural networks in encoder-decoder blocks, and condition single-agent reinforcement learning policies on them. However, these approaches acknowledge that the learned policy can struggle with long-term dependencies, handling noise, and assumes that the learned latent variable is Markovian. Our approach utilizes a transformer to address these issues. To address the problem of predicting a changing human behavior, we assume that the human behavior is governed by a latent state Z. Under this assumption, the human policy depends on the latent state Z and current physical state S. This makes the environmental dynamics constant over time given the human's latent state Z. The latent variable represents the high-level human target. Therefore, to solve this problem, the latent variable needs to be inferred from the history of interaction between the human and the robot. To train the policy network with reinforcement learning techniques, it is required that the environmental dynamics are Markovian. However, the variable Z may not follow this pattern. To address this, a latent state phi is learned that is Markovian, enabling optimal policy convergence. Hence, we define a new state, S of phi, which is the concatenation of S and phi, that transforms the transition dynamics to exactly the same as a single-agent Markov decision process problem. This enables the application of traditional reinforcement learning methods by turning the problem into a single-agent reinforcement learning problem with an inferred Markovian state representation. Hence, the focus of our work is to estimate a variable phi that is latent and its evolution follows a Markov process. To learn the Markovian latent variable phi, we need to compress the historical information into this representation. We use a transformer to do this due to its effectiveness in learning semantic relationships from historical information. The transformer was trained in two phases, a pre-training phase and a fine-tuning phase. In the pre-training phase, the losses from predicting the state, action, reward, next state, and whether the episode is done were used to update the transformer's weights. The purpose of this phase was to train the transformer to learn the underlying structure of the data. In the fine-tuning phase, the predicted latent variable is fed into the dynamics network along with the corresponding states and actions. The dynamics network is a feed-forward neural network that allows us to reconstruct the transitions and rewards for our loss. This allows the transformer to learn a latent state that makes the dynamics Markovian, and we name this approach B-trans. This is the overall system diagram. For the reinforcement learning element of our approach, we use the soft autocritic algorithm. With B-trans, we infer the current latent state phi from a history window of desired length, and the policy executes an action given S of phi. The action network requires S of phi to be Markovian. Experiences are stored in a replay buffer during execution, and then sampled at random from the replay buffer to update the soft autocritic and transformer weights. For the data generation, we developed a probabilistic human agent model with three key attributes, including a time invariant component, such as right-handed, so biased towards forehand, a low-frequency history-dependent component, such as being tired, and a high-frequency history-dependent component, such as hysteresis, so biased towards selecting previously successful actions. Each human agent's behavior evolves as a function of these attributes and its experience over time. To evaluate our approach against baseline methods and produce a platform for investigating hypotheses, we developed a custom environment named CoPass. This allowed us to evaluate whether a robot could adapt to changing human behaviors during an episode in the presence of observation noise. We discretized the state space and varied both the number of target locations and time steps over which the ball traveled between paddles. The dynamics were deterministic, with the ball changing direction when it hit a paddle, and the subsequent trajectory being a function of the paddle's orientation. A point was awarded for each successful intercept of the ball, and the goal was to accumulate as many points within a set time frame. We compare our method against 4 baselines, including Oracle, which knows the human's ground truth latent state and provides an upper bound for our method's performance, Soft-Critic, which is a single-agent reinforcement learning method, Lily, and RNN-Lily, where feed-forward and recurrent neural networks are used to predict the human's latent state. We run 4 experiments to see how well our method deals with noise, adapts to within-episode human behavior changes, and captures longer historical dependencies. In the first experiment, there was no noise, and the human's agent score was constant during episodes. B-trans converged faster to the optimal policy than baseline methods. In the second experiment, noise was added, and it is seen that B-trans is robust in handling observation noise. In the third experiment, the human behavior changed within episodes, and B-trans was able to leverage its flexibility to converge to an optimal policy. For the fourth experiment, we investigated longer histories, and B-trans could more effectively capture long-term dependencies. In conclusion, we created a framework that can learn optimal robot policies in human-robot agent collaboration scenarios where the human agent changes behavior. We validated our method on a novel environment with customizable parameters and over a range of simulated humans with biases but Markovian behavior in fixed windows. Our methodology allows the robot agent to adapt to changes in human behavior through learning a representation which makes the environmental dynamics time invariant, thereby allowing the application of single-agent reinforcement learning methods. It outperforms baseline approaches, can handle noise, adapt to changing human behaviors during an episode, and effectively captures historical dependencies. For future work, we intend to extend our approach to non-Markovian behaviors and train the method using actual human data. Thank you for listening.